Hello, I welcome you all to this another interesting screencast. The problem reads that the spring bumper is used to arrest the motion of a 4 pounds block which is sliding towards it at the speed of 9 feet per second. As shown, the spring is confined by the plate P and a wall using cable so that its length is 1.5 feet. If the stiffness of the spring is K equal to 50 pounds per feet, determine the required unstretched length of the spring so that the plate is not displaced more than 0.2 feet after the block collides into it. Neglect friction, the mass of the plate and spring, and energy loss between the plate and the block during the collision. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Benam. Let's draw the free body diagram. So we do have the weight, okay, and we have the normal force, like so. So this is our normal force, and this is our weight. Okay, let's clean it up there just a little bit, and there too. All right, so what else? So let's say, of course, this particular spring, when you look at this spring, it is already displaced by these strings or ropes. You've seen these ropes? They've already compressed this particular spring by a certain length, okay, or displacement. Right, so we need to take care of that stretched length as we do the calculation. So let's just indicate really what is happening. So let's say we have, let's say these are the points where the spring will undergo some displacement. Okay, let's say that is the point, like so, like so. And then this point, let's call it 1, and then we call this point 2. So we want to move the spring from 1 to 2, but mind you, like we said, the spring is already displaced by a certain distance or certain displacement, which we do not know, which we're just going to call S or X. All right, so therefore we can simply say, I'll use X instead. Our initial displacement is L node, which is the original length, okay, or instead of calling it like that, I'll just call it let me call this instead S. So I'll say S1 is just equal to X, okay, which is my original length minus 1.5, okay, 1.5, where X is the original length of the spring. Okay, is that okay? Yes, and therefore our final displacement S2 is just going to be equal to S1, okay, this S1 plus this S1 plus S1 plus, where is it? We've been given the displacement. Yes, S1 plus 0.2. So this one is the displacement that our spring has undergone. All right. So this one here is 0.2. 2, right? Okay, right. So with that information, we intend to use the work and energy principle. So we are saying the initial kinetic energy plus the total work is just equal to the final kinetic energy. So we do have our initial velocity there. So we can simply say half m v1 squared plus integral from S1 to S2 of the spring force Fs ds is just going to be equal to 0. Why 0? We are saying this is momentary. It is momentary 0 because it is momentary it momentarily stops. It has momentarily stopped. Okay, so this is a case where the spring is compressed, and then at that point where we reach the maximum displacement, we momentarily stops. We stop. So that is where we are considering. That's the reason we are saying at that particular point where the spring has the maximum displacement, it's about to get back. At that very point where it stops, that's a moment. It has momentarily stopped. So we are saying the kinetic energy at that point is equal to 0. So let's work with this integral. Okay, Fs. Mind you, we said before I write this, we said S1 here is equal to x minus 1.5. Okay, and then S2 is equal to S1 plus the displacement 0.2, which is just equal to x minus 1.5 plus 0.2. And therefore our S2 just becomes x minus 1.3, right? Great. Therefore, our integral from S1 to S2, Fs ds, I'll write in terms of dx instead. So we have x minus 1.5, then here x minus 1.3, then minus kx, okay, because we know that our spring force, so we are going to have a force. The moment this particular block strikes the spring, we'll have a force on this part like so, and also on that part like so. All right, and this is our Fs. This is our Fs, and this one is just going to be equal to Fs is equal to k times x. Okay, so this minus here takes care of the signs for our work done by the spring. Okay, so the important thing is to make sure that you get S1 and S2 correctly, right? So instead of the S here, I'll just say the X. Okay, again, there's really nothing wrong. If you want to integrate with respect to S, well and good. Sometimes S just looks like 5, so I prefer just using other letters. Alright, so this therefore just becomes, if we integrated this will be k s squared divided by 2. Evaluating this at x minus 1.5, right? And this one x minus 1.3. Okay, so this therefore just becomes equal to our stiffness. The spring stiffness is 50, so we'll say 50 divided by minus 2 like so. All right, then we have x. We do have there x minus 1.3 squared minus x minus 1.5 squared like so. Okay, So this therefore just becomes a minus 25. There we go. Then this we have x squared plus 1.3 squared minus 2 times 1.6, 2 times 1.3 by x, which is a 2.6x, then a minus there x squared, then a minus 1.5 squared, minus just becomes a plus 2 by 1.5, which is just a 3x. Okay, so this and this goes, right? Then we have, let's work out, the minus 2.6 plus 3 by 25, which is a minus, so this is minus 10x, 1.3 squared minus 1.5 squared, and then times 25, this is a positive 14. So now let's replace this in our equation, which is just half mv1 squared plus our integral that we had written initially, okay, equal to 0. So here we have half, let's borrow some space the other side, maybe, since we still have space. So we have half there, and our mass is 4 divided by 32.2 times the velocity, which is 9 squared like shown, then minus 10x plus 14 equal to 0. Okay, let me just push it a little bit like so. There we go. Right. Right. So making x subject to the formula, this is just going to be equal to, you can grab your calculator, so 0.5 by 4 divided by 32.2 by 9 squared plus 14, then later on divided by 10. So this gives us a 1.9031. Alright, so we said x is the original length of the spring. Therefore, our x is just equal to 1.90 feet. Right. I guess we are done. Let's just outline our final solution. I guess we are done. And I hope this video was helpful. And if it was, give me a thumbs up, like the video, continue subscribing and sharing, liking my channel. Bye bye. And I'll see you in my next screencast.